All right, I say we should get started. Before jumping into the code, which will be 95% of this lecture, I want to tell you a couple things. Just let me drop a marker that works. All right, so we concluded our overview of concurrent sim.jl. We saw the strength points, it's general, it's efficient, discrete events, nice, good. We also saw the pains of working with something like that. Yes, it's very bare bone. We have to work with processes. If you want to model some complicated distributed system with a lot of synchronization going on, like that repeater chain, it's a lot of work and it's very prone to mistakes. This is why if you actually want to simulate complicated and large distributed systems such as networks, what you usually do, you work with simulators that are built on top of a generic discrete event simulator that supports specifically network simulation. And this is true for both classical networks and quantum networks. So if you look at in the industry and literature, for example, for networks, you're going to see Omnet++, which is in C++. You're going to see NS3 and others, which we don't care about right now. For quantum networks, there is several. There is QuantumSavory, of course. There is Sequence. There is NetSquid. You might not have heard of any of this. There is Quiz. What all of these guys have in common, which makes this introduction general, not only to QuantumSavory, but all of this, is that you want to work you want to design your simulation at a level that is more convenient than what we have been working so far with concurrency. And the way all of this, in the way the standard approach to do this is to model the network in two phases. So when you want to simulate a system, there's something that is intrinsical. So if you look at the network, there's something about the network that is intrinsically true, independently of what you want to simulate on top on the network. And that's the hardware, that's the topology of the network itself. So what's the layout of the network, where are the nodes placed, what are the hardware capabilities of each node, what do the links look like, who can communicate with each other, what are the classical latency delays, and so on and so forth. Then what I want to do on the network on top of that, it's up to me. So what we're going to do is, like the paradigm we're going to follow is modeling in two steps. First, we describe the network that we want to simulate. Then, on that network, we install dynamic behavior. We install protocols, and in terms of concurrency, we install processes that use that information on the static topology of the network as convenient API to do things more easily than before. It's going to be a smoother way of working with the network simulation, and hopefully less prone to errors. And this is for what concerns, in general, network simulation. So this is the approach we're going to take. Now I want to take a couple words about quantum network simulation specifically. And this is specific to QuantumSavory. And the way you can see the whole thing of simulating quantum networks as simulating, as I said before, a big LOCC with a lot of communication steps. And this is going to be a large distributed multi-step LOCC operation. And you want to derive at the end of the day, what is the quantum state that comes out of the network? And it might be a distributed state across a lot of nodes at the end of the whole protocol. It might not be a quantum state. It might be a set of measurements results. It's up to you. You might want to repeat that experiment several times to collect many independent samples. So this is what we want to do. And now, an LLCC, you can break it down in two sets of operations that are related, but they're different. So there is an LLCC is, I repeat it if someone wasn't here, local operations and classical communication. So at every step, so say we have a network, right? So this is the static description of the network. We have a bunch of nodes and a topology that connects them somehow. So this is my network. The dynamic behavior is going to be the LLCC. So, and it can be described, for example, as follows. Step one, distribute entanglement between these two guys. So I write LLEG, link level entanglement generation. So the entangler protocol from the simulation before. So we wait for, and what happens is, I put it in a single step. This might, if you simulate a really low level, it might itself be broken down in several steps of communication, because you might have to, for example, do a preliminary handshake to synchronize the nodes and do stuff. We just assume it's an atomic operation. Step two, and this is swap at this guy here. Entanglement swapping, right? What we did before. Now, before you can do swap two, step two, this guy has to have the information from that about the fact that he's now entangled to both these nodes, to both these adjacent nodes. So there is going to be implicitly, there is some causal dependency. You cannot go to step two, you cannot implement step two right away. There is some classical synchronization that can be implemented through classical messages that have to go on to go from step one to step two. And once this has done the swap, the state of the network changes. This guy are actually entangled now. And step three, application. The application that runs at Alice and Bob implements whatever protocol they want to do with that bell pair. Okay. So this is classically what are the dependencies and what in time is happening. So we have a phase of entanglement distribution. It takes some time, some synchronization phase. We go to step two. This guy swaps, and the communication out, the measurement outcome to one Alice or Bob. We wait again a little bit, and then the application consumes the bell pair. We're done. Classically, we can see things like this. At the same time, in parallel, we have a quantum state in the network. So we have to track what this qubit is storing at any given time. And for example, before step one, there are all a bunch of qubits uninitialized. After step one, we have a bell pair here, say 5+, which might be noisy if we want to implement noise. So this might be a density matrix with some noise in it. And there might be many of these around the network, and we have to track the whole quantum states down, because at the end of the day, we're going to do measurements, and we might want to track the fidelity. So if we have a bell pair, one bell pair for the link, for the first link, another bell pair for the second link, the memories might have some decoherence, so they might have decohered in the meantime. So once we get the final state, it might not be perfect anymore. And the outcome we might want to measure is the fidelity of the resultant state. That's a pretty common thing to have. And this has to be supported by a quantum, like I'll call it quantum backend. So now you should see where I'm going. So the whole classical interaction and synchronization is not anything else but the discrete event simulator we have been seeing so far. The quantum backend that monitors and tracks down the state, and it's smart enough to track down whether things are entangled or not, trying to factorize as much as possible the different memories in the network. This guy here, it's up to us. This guy here can be anything we want, but what I want to mention is that it's separate from the discrete event simulation. The way we try, and they communicate. Because, for example, this guy here, once we are at step 2, this step 2 has to inform the guy that now we are, say, time equals 42. So it should now evolve the quantum states in memory so that they decohere up to that time, for example. So they have to communicate, but they're intrinsically different objects. And we're going to work with both. We're going to start from the quantum part. To finish, this guy here in QuantumSavory is not atomic. It's itself composed of 2 parts. And this is the key, the key element of QuantumSavory. This guy, the quantum backend, is based on a symbolic front end and let's say any backend. What this means is that user, you are the user, you want to use QuantumSavory, you model your states in the network and your operation using symbolics, using LaTeX equations. You just describe what you want. So you have no idea how internally the states are represented or executed, or the operations are executed. So you just model your states and using the symbolic front end. And this is offered by QuantumSavory through the QuantumSymbolic.jl library. Then internally, you can, QuantumSavory chooses, and you can also explicitly set it, you can choose the best backend given the operations that you're doing. So for example, if I'm only doing Clifford operations, I might choose to represent all my states with a stabilizer representation with Quantum Clifford. So indeed, Quantum Clifford is one of the standard backends that you can implement. If you need something more general, you can use quantum optics, because that is basically state vector or density metric simulation. Those 2 are usually the most typical things you want to do. Again, if all of your states you have in simulation are Gaussian states, you might want to use GAPS. That's another backend that's specific for Gaussian quantum states. And finally, tensor networks. I don't know that that's already in there, but it's in theory possible to add a backend that works with tensor network representation, and if the operations you're doing are suitable for that. And this is the major selling point, because it's gonna, if you want to switch the different backend at any point, you don't have to change anything in your code. You can just plug in a different backend whenever you want. So the goal of today, and we're going to go through how to use this, the symbolic, how to plug in different backends. It's literally 1 line of code. And then we're also going to see the discrete event simulation part, but for this, it's basically the same as concurrent sim. It makes it a little fancier, but concurrent sim is what runs underneath it. So let's move to the code. Okay, you know what? Let's turn it on. Sorry. Sorry. Okay. Is it visible? Is it large enough? Okay.
Can you make it a little larger?
Yep. Okay. So as I promised at the end of the previous lecture, I'm going to start with a show-off example where I just show you how to set up an arbitrary repeater chain that can generalize to any arbitrary topology actually in just a few lines of code with QuantumSavory without having to worry about without having to worry yourself about any locking resources, resource contention and so on and so forth, synchronization, etc. So let's see how we do it. If you don't understand some parts of it, don't worry because we'll break it down and go over every single part of this example later on during this 3 hours. So at the beginning, we import a bunch of we're using a bunch of libraries, the most important of which being QuantumSavory. And QuantumSavory's protocol zoo, that is basically the API of ready-to-use protocols for quantum networking. And not only quantum networking, it can be also other things, whatever you can do with a quantum network. There should be also some sensing protocols, etc. So as I said, the first thing we want to do is phase 1, describe the network. So the static part, right? Well, let me snooze pilot. So let's set a bunch of variables. So we have a 5 nodes chain. We want to set a success probability for swaps. We set it to say 0.2. We want to set an attempt time for link level entanglement generation. So every time we attempt, this is just an example. I mean, we can come up with different parameterizations. Let's specify a seed. Okay, so this is boring stuff with that. So now, how do we instantiate a network? First of all, we create a graph of that. We represent the topology of the network using graph from the graphs library in Julia. We can use this, and it's basically the same as network X in Python. It has the same kind of structure. You can do sort of roughly the same things. So we want a repeater chain, right? So the way we do it, the simplest way to do it is to build a graph as a grid with 1 dimension. So this is going to be a grid with n nodes. So this is n nodes by 1 grid. So a chain. So this is our topology, logical topology. And then we want to specify this, basically we want to specify where the quantum systems in the network are placed. And this is what we call registers. In our case, the registers will be placed at each node of the network, right? Each node of the chain will have some quantum memories. So basically our registers will be an array of register with how many qubits? Let's say 2. So every element in the array is a register with 2 qubits. 4. in 1 to n nodes for every node in the network. So we have a register, we have our so this specifies what nodes are in the network. This basically tells you how those nodes are connected to each other. And now we create a network. So our network is a register network. It's a register net of a given graph. And we pass registers. That's it. So the way it assigns registers to vertices in the graph is by indexing. So the first, the vertex with index 1 in the graph will be basically mapped to the first element in the register array. And so on and so forth. So we have our network, and now the only thing that's left to get is a reference to the simulation object. And we have a function for that, get time tracker, to which we pass the network. So we're telling QuantumSavory, we want to simulate this topology here. All right. And if you look at it, it returns a concurrent simulation object. It's just a wrapper around that. Okay. So the static part is done. We created our topology, we modeled our quantum hardware in a very high abstraction level. And now we have to tell QuantumSavory what we want to simulate on it. So what we want to simulate is entanglement distribution. So over time, we want to create link level bell pairs, swap them out, and create as many end-to-end bell pairs as possible over time. So let's try to do that by using, as users of QuantumSavory, let's just limit ourselves to use what QuantumSavory already offers to us, which is a lot already. Yeah.
Are the registers memories?
So the registers themselves are, you can see them as nodes. The memories are the slots within the registers. So register 2, it means that this will be a register with 2 memory slots. And each memory slot can either be a qubit or, as we'll see later, any other, an harmonic oscillator, whatever you want. Blah, blah, blah. Okay, so yeah, so what do we do? So basically, if you remember the implementation for the repeater example, we have to install some processes. So that's what we're going to do, basically. Ideally, we want to install a swapper, a repeater protocol, a repeater process on each node of the network. And we want to install an entangler process on each link, on each edge of the network. So that's ideally what the following code will do. So for every edge in the network, and the way we iterate over that is like this: source, this destination. So we unpack the edges of the register network. Okay. For each one of these guys, we create an entangler. And this is where the QuantumSavory becomes useful, because we have already for us an entangler protocol defined for us, which is nothing else but a process, a resumable function. It looks like an object because it's basically a callable struct. That's what protocols are in QuantumSavory. Protocol is a struct for which we define a function that turns that structure into a resumable function, basically. And so it's basically a fancy way of passing some shared context to a resumable function, but we'll get into it later. So just see it as a resumable function. So our entangler protocol is our process. And what will it take as parameters? As we saw before, it will take a reference to the simulation. It will take a reference to the network we're simulating. And it will, the entangler, basically the important thing that you need to know is what 2 edges, what link it's working on, right? So the identifiers of the 2 edges it's working on. So it wants source, and it wants destination. These are all the mandatory parameters. After this, there's a bunch, and you can check the docs for this, I can show you later. there's a lot of configuration parameters. You can configure this entangler protocol to be as realistic as possible to include all sorts of delays, noise, success probabilities, deadlock, dead times, and so on and so forth. We will keep things simple here. We will just set the success probability. We'll set the attempt time. And now the only other thing we need is, which is something you would have had to encounter if you try to implement that on concurrency, is something that will prevent deadlock in the network. So let me just write it down and then I'll tell you what you're doing. Choose slot equals 2 and choose equal 1. I'll draw it because it's easier. So basically if you have any two nodes in the network, we have one node and the other node and the link connecting them. Each one of these are going to be register 1 and register 2. Okay, each one of these guys each one has two memories, one on the right and one on the left, 2 slots, right? Because that's how we define them. So this entangler, the entangler protocol we are launching on this link, when it tries to lock and reserve a slot on this guy here, it will try to reserve the right one. Okay, so this is why choose slot A sets it to 2. We want to try to reserve only work on the second slot of the left node, and we only want to work on the I don't know what I said. We want to work on the right slot of the left node, and we want to work on the left slot, so the first slot of the repeater on the right. So that's what choose slot is doing for you. It's forcing entangler protocol to work on these 2 slots specifically. You can pass predicate functions if you want, like if we had multiple choices, you could pass, okay, any slot greater than 2 works for us. So if we have multiple slots, you can also configure it so that you can partition memory slots the way you want. All right, so we created our entangler protocol. We just launched it as a process. Okay. So now we uploaded basically a bunch of entanglers and all the links. So if we launch the simulation now, the only thing that would happen in the simulation is all the links would get entangled and no one would swap because we have to install the swappers. So this time for the swapper, I'm going to paste the code. So for the swappers, we have to install a swapper on any internal repeater of the chain, right? So every node except for the 2 end nodes. So for every node from 2 to the second to last, we install a swapper protocol. The parameters are always the same, simulation and network, always. We specify which node this swapper is working on. And now we have to tell the swapper what nodes we want to entangle. And so basically, because QuantumSavory for you, there is some metadata tracking, and we have a way of knowing to which node every memory slot is entangled with whenever it gets entangled by an entangler protocol. We have a tracking system going on. So this means that wherever qubit on the left we choose to swap, that has to be entangled with any node whose index is lower than the index of this node. So basically any node on the left of this node on the chain. And the node high can be any node that's on the right of this node on the chain. Do you want me to draw this or is it clear? Okay, I'll draw this. So say we are this guy, repeater 2. We install a swapper here. Okay? So the swapper works whenever it tries to, somewhere inside the swapper, you're going to try to lock these two qubits when they are ready for entanglement swapping. So the way you pick a qubit is that this guy is good as a right side qubit for the swapping only if it's entangled with any node that's on the right of this. So any node that's towards Bob. The other qubits, it's only valid if it's entangled to any node in the network that's on the left, so towards Alice. So that's what that predicate does. And finally, and this is for every node in the network, we need to install an entanglement tracker. Because as the simulation goes on, and this is for classical, for tracking the entangled state, not the quantum backend. This is for the classical communications required to track who's entangled with whom. We want to install an entanglement tracker protocol that basically monitors the network, who swaps with whom, and so tracks, marks, registers lots, informing people about what every memory slot is entangled with what other memory slot in the network. So this is a guy we need that will work in the background and will just take care of having everyone informed about what's going on. And all these protocols here, entangler protocol, swapper protocol, and entanglement tracker, and entanglement consumer come together as a suite of protocols. It's an API. Whenever you want to work with them, you install all of them, and they guarantee you a certain kind of service, which is what we are going to get, end-to-end entanglement distribution. Entanglement consumer is simply the application. Whenever you have entanglement within Alice and Bob, and they're directly entangled, you measured out those qubits and you're happy. So this is all. I will now do this. So we just need to run the simulation. However, what I'm going to do now, I'm going to run it in time steps. What we're going to use a visualization API that QuantumSavory gets shipped with, which basically allows you to take snapshots of the current state of the quantum network at any given time during the simulation, and have a literal picture of what the network looks like. And it's very good for debugging and for presentations. And what I'm going to do, I'm going to be filming a movie, because I'm going to take a picture every few units of time to see how the network evolves with time, to show you what is actually happening physically in the simulation. And indeed, the output will be an MP4 file. And you should be able to see it. Maybe not very visible. And maybe yes. Let me show you directly the MP4. No, much more visible. But you see that the links get created, and then they get swapped, and then very quickly, as soon as an end-to-end link gets created, it gets swapped right away, disappears because the consumer consumes it. So every time they all disappear, it's because an application has consumed the bell pair. So here you can see the network delivering bell pairs over time. You see the counter moving up. Okay. So this is what a full stack, let's say, simulation of QuantumSavory looks like. there is a lot that you can do by just configuring these protocols to what you need, hardware-wise. But there might be situations where you need to do something different. So you can, the way they are developed, you can replace each one of these protocols in the suite with whatever custom protocol you want and implement any custom behavior. And this is just for entanglement distribution. There's other things going on for every different kind of things you might want to do with a quantum measure. So what we're going to do now, so this, we took a top-down approach. We started from the very top thing you can do full stack. Now we're going to go bottom up. So we're going to dissect every single component in QuantumSavory, starting from how you model quantum states with the symbolics API, which we did not tackle here at all. The symbolics were all embedded within the implementation of these protocols.
So I want more speed than this side, that side.
Oh, while Julia decides how long it's going to take to start. So the way we model, like cat states, I mean cat is already a representation. So the model the qubit states is the syntax is as follows. So you define your whatever variable, psi will have Z1, say. Z1. This means this is the first eigenvalue of the Z operator. So it means it's going to be cat 0. Okay. So this is the notation we use in symbolics. Whereas, for example, phi equals x2. This is the second eigenvalue, eigenstate of the x operator, which is going to be minus. So this is for states. For Pauli operators, of course, you can just simply type x, y, z, or h. C naught is already there. And if you look at the REPL, what it prints, like there's nothing about how they are represented internally. So this is just purely a symbolic name for this state / operations. It's the conversion to an actual representation is going to come later, only when you need it. And for example, C phase, for the full list of guys that you have by default, you can go look up QuantumSymbolics.jl. There is a whole list of the reference APIs. But the nice thing is that you can combine it with tensor products and so on and so forth, right? So let's try to see how we do that. For example, we can get product state by getting the tensor product between Z1 and X1. And now, the first non-trivial state, we can create a Bell state. So how we define a Bell state? Well, Bell I plus, see if I can do it. That's plus. Well, it's going to stay like this.
You need to do /phi and then add another slash before doing the caret plus.
Gotcha. Let's try that. Another slash here, right?
Yeah.
Okay. Plus. Thank you. So how we define it? Well, it's going to be Z1 tensor product Z1. It's 0, 0. Plus 1, 1. So Z2 tensor product Z2. Normalized, so we have to divide it by square root of 2. And this is a Bell state. Again, symbolic representation. These cats here, they're not represented, it's just a name, they're just labels. Now, the library is also smart enough that it can also simplify the symbolic expressions that you have in your modeling. So for example, if I want Adamart applied to Z1, this is going to be the plus state, right? And it's going to be an error because I didn't put this here. There you go. So this Adamart applied to Z1, we know that it's plus. So what we can do, we call Q simplified. Test this. And this turns into X1. So it's sort of a black box to simplify. You can use it to see if there's an easier representation for what you have already written down. Let's start talking about density matrices. We're not enforcing a density matrix representation, but we're going to talk about mixed state, more precisely. So to do that, it's convenient to define the projector, because a projector on a specific state psi is equal, you define it as using the S projector object, symbolic projector. And you pass the symbolic representation of whatever state. And in this case, psi was defined as Z1. So this will be the projector on Z1, the projector on cat 0, basically. And it lives in the space of projectors. So this is the syntax. And if you want to get a completely mixed state, it's simple because you can just call mixed state. And you have to pass the dimension you're working with. So the way you can do it, you can pass another state and it will create a mixed state of the same, that lives in the same space. So I can just pass, I don't know, I can pass Bell. And it will be basically a 2-qubit completely mixed state. So now we have all the tools, for example, to define Werner states. So if I want a depolarized Bell pair, the depolarized Bell pair will be some probability, say 0.8, with 0.8 probability, it's in the actual Bell state. So Bell, we have to work with projectors. So it's 0.8 probability is in S projector. Oh, we have it. No, we don't. S projector of Bell, right? And with the remaining 0.2 probability is in the completely mixed state, which is the one above. And here is our depolarized Bell pair. You can also define commutator between operators, commutator between, say, X, Y. You can define Of course, the dagger, a joint dagger of say X H dagger, which happens to be the same. So if I call Q simplify, let's see if it's smart enough. Q simplify on dagger of H. Yeah, it's not that smart. All right, so this is for what concerns expressing states. Now, later on in a second, we're also going to see how to apply complex operations and evolve states over time. But this is for modeling states. This is enough for now. So now we have our symbolic representation of the state. How does that symbolic representation get converted into what actually happens in the quantum backend that actually runs the quantum part of the simulation? So that's the key function, the key API is the function express, which in QuantumSavory you will never have to call yourself. The QuantumSavory does that for you. We're just dissecting what happens internally here. So if you express Z1, let's just express it for by default. If you see, what representation is this? You have encountered in this summer school once first.
State vector?
Yeah, it's a state vector. It's a cat. And that's the default. If you don't say anything, I can force for representation. Apparently I cannot. Did I? Oh, I didn't import it probably.
I think you missed a D in Clifford.
Oh, there you go. Thank you. And there it is. Same guy, different representation. And we can play with the rest of the states. For example, express. Let's look at the depolarized bell pair. Express. Oh, what did I call it? Depolarized pair. Let's see. So by default, since it's depolarized, it's not a pure state. It will, if we use the default representation, it will switch to a density matrix. If you use the Clifford representation, because this is still a state that representable using Clifford representation. No, it's not. Yeah, it cannot. I was joking. Yeah. But yeah, it wasn't this. Anyway.
Excuse me.
All right. So you have to be a little careful because, yeah.
Oh, sorry. I just had a quick question about how you define the depolarized bell pair state.
Yeah.
So there's the S projector function, and I understand that's like psi plus outer product psi plus, right?
Yes.
What is mixed state of psi plus?
So it's a completely mixed state of that same size of the matrix.
Okay.
If you use a matrix representation of the state you pass to it.
So this is the maximally mixed state, and all you're taking from bell psi plus is or phi plus is the size.
It's a size, yeah,
Okay.
yeah. It's the only thing you care. I don't know if there's another constructor for mixed state, but it's usually you can do this.
Okay.
Yeah.
Thank you.
Of course. Fancy thing, we are not limited to qubits. So for example, we can have Fox state. And we can apply the number operator. And yeah. And if we simplify this, it will be smart enough, hopefully, to understand that this will just leave the state unchanged. It is. So let's see what express does. So if we try to express this Fock state, let's see what he chooses to represent it. It's a cat state of size 3. So this means that by default, it cuts off the Fock basis at 2. Yes. We have 0, 1, 2. Yeah, everything at 3 and above, it gets cut off. If you want, you can specify a larger cutoff. And the way you do it is with express one photon quantum optics representation. And you specify a larger cutoff. Say cutoff equals, I don't know, 6. Yeah, and that's a larger cat state. And the same express thing works for operators, of course. So like, for example, I can express the number operator in the quantum optics. And you can see that it's an operator. And in this, the whole package is smart enough to understand that it's parts. So you see there's dots. It's smart enough to understand that it's that it can be represented efficiently. Okay, now I'll move on from this. We'll hopefully do something that's a little more fun. But before we do that, little mini assignment. Let's try to follow this. So I want you to build Hadamard applied on cat 0, simplify it symbolically, and the output you should print it, express it, and see, you should the output should be the plus state, of course. Let's see if you it should be like pretty simple. And then try to build the density matrix that is 75% the pure state that you get from the point 2 and 25% the completely mixed state. And then express them in both representations we saw.
Yeah.
Give it a couple minutes.
Check.
For the crystal representation, you should express the before you do the density matrix thing.
Yeah, that's true.
How are we doing? Got it? Well, I'm gonna paste what I did. So counterpart applied from 0, get 0, it's C1. Yeah, whether you put it on the index or you just write C1 is the same. This is AC1, then you simplify it, turns into X1. Then you build an density matrix using 0.75 the projector on the actual state and 0.25 the completely mixed state on the same space as the state that you have. And then we express everything. Okay. So we now covered the very basics. Now we're going to go a step up. You remember when we instantiated the network, we were talking about registers, right? So what we're going to go over now is the register API. And everything, or almost everything we can do with registers, and how to manipulate quantum states, how to evolve quantum states, and what we can do with it. So let's take a look. So the way we define a register is pretty simple. A register, you can call it with register. Then you pass the number of qubits by default. This is a register with 3 qubit slots. So you can store at most 3 qubit states. You can index it. So this will access the first slot of that register. And the type of this should be a register ref. Not that you particularly care, but that's what it is. Yeah, that's what it's called, register reference. I'm telling you because you might encounter this type later. You know what it is now. And you can also access subsets of that register. So if I want 2 to 3, that's going to be a 2-element vector of register refs. Now, this is the most basic way of instantiating a register, but something a little more articulated you might want to do, you might want to have a register with a qubit, a Q mode, and maybe another qubit. So this means that this register can store 2 qubits in slots 1 and 3, and bosonic quantum modes in the second slot. So this is how you create the register. Now those slots are empty, right? So we want to put quantum states and manipulate quantum states inside those slots. So the way you do it is using the initialize function. This initializes an unassigned. So if you run at the beginning, if you write is assigned register, say register 1, it returns false because nothing is assigned at the beginning. But if we call initialize register 1, so the first slot, which is a qubit, we initialize it with, it has to be a qubit state, so let's say Z1. It did not like it. We did not import QuantumSavory.
I in initialize.
Oh boy, thank you. Yes. There you go. Thank you. So now, if we want, we know that inside that register, we're going to have the cat0 state. Of course, you can initialize it with any state you want. We can, for example, if we want to initialize 2 register slots with a Bell state, you can call initialize. On 2 slots, now this is assigned, but let me create another register. With 2 qubits, and we should initialize register 2, we can use this compact. We can pass a vector, so 1 to 2, the first 2 slots in the bell state. And now we put a bell state in memory. Now, ideally, usually you're going to do this on register slots that are in different registers because you want to initialize the geographically distributed entangled states. So if you have 2 registers, so reg 1 was this, actually, register with 1 qubit, 1, and reg 2, another register with 1 qubit. I can call initialize. You can pass a tuple, so I will initialize reg 1, the first slot, and the first slot of reg 2 in the bell state. And that's how you create a bell pair very easily. If you want to pass, I mean, we might have initialized them with an imperfect bell pair, and we might have passed the depolarized bell pair from before. I won't do it because it's more of the same. All right. So now, let's try to start inspecting this register. So like we know that inside that register, that's what that register contains. The way things are stored, you have to. So this is not how you're going to do in the code. I'm just going to show you, just so you know how things are actually stored inside. If you want to access the actual, because the moment you initialize, you are basically forcing QuantumSavory to express this state and store it in the register using that representation. So this state is now not symbolic anymore, it's numerical. So now this numerical expression of the state should be somewhere stored in the program. And the way you access it, if you want to exact representation, is like this, right? There is a field state references, and it's a vector, so we want the first element of that, and then we want access the state of that, because itself is an object. What did I do here? It's weird. Did I initialize it? Yeah. Oh. Let's see what's inside this. It's nothing. It's
So you have a register.
yeah.
Initialize.
Oh, yeah, I didn't put the 2 here. There you go. Yeah, that's why. So if I put register 1 here, then
and you are also using the index 2. I think you need to use index.
Oh, I put the 2 here instead of before. Yeah, gotcha. So anyway, I will inspect this guy here now because we know that there's something in there. Reg 1, thank you. Reg 1.
Since you have initializing a multi-qubit states on 2 separate registers, does each register have a...
No, yes, it's smarter than that. It's somewhere in the numerical backend, we store that state only once, and it will know that it's shared between those 2 registers. If for any reason they are going to disentangle, it will also factor them out and start storing them separately again. It was smart enough to try to factorize as much as possible the quantum state.
Is this with a specific simulation backend, or are we still using it or are we still using some native kind of?
That should that's a good question. I think it's for each simulator. For sure, it works with for sure it works with the quantum optics and quantum Clifford for those two. For those two, that's how it works for sure.
So are we using the quantum Clifford simulation?
Oh, we are not specifying here, so we are using quantum optics. If you're not saying anything, I'm going to show you how you can change that in a second. Yeah. State refs. Oh yeah, here. Okay, we did it. Okay, so and this is why you don't access this, because it's prone to error if you do things this way. If we inspect manually inside, we can find actually representation of that state, and it's a cat. That means that somewhere we have chosen to use the quantum optics representation. What you want to do is not this. If you want to inspect the state and do things with state, you want to work with measurements and observables. So ideally, you want to, for example, let's get the expectation value of some observable. So observable. This is the function observable returns the expectation value of an observable on a state without altering the state itself. So it's not actually measuring. So we can just simply pass this here. Yeah, and it's basically one. So this is the proper way of inspecting state. Now, to answer your question, how do we set custom representations? So it's in the register definition. So at the beginning, if I define a register, this is going to be a register of 3 qubits. And all 3 qubits will use Clifford representation. You can also vectorize it, so I can pass a vector of 3 qubits, and I can pass a vector of representations and use different representations for each qubit. That's totally allowed. The only thing is that you're not allowed to entangle those qubits, because cross representation, if you have an entangled state that crosses representation, that's not allowed. It's not going to be able to do it for you. So as long as they don't interact, you should be fine, but you should also be careful. Okay. So this is on how we start out. We create our registers, we load quantum states inside them. Now to evolve those quantum states, we have to apply operations, right? And so let's create a new register for this purpose. So I have a gate reg equal register with 2 qubits. We can, let's initialize it. Just this. We put cat 0 everywhere. Oh, okay, we put cat 0 everywhere. And now we apply, and this is the API. To apply an operation, you just call the apply function, and it has an exclamation mark because you're actually changing the quantum state now. And we apply on gate reg 1 and 2, because we want to apply it on both qubits, we apply C0. And this does nothing because the input state is 0, 0. But of course, you can, for example, let's build a bell pair. So instead of initializing the 2 registers in a bell state, let's create the bell state but by operating on this state. So we first apply Hadamard on the first qubit. And then we do the C0. And now we should have our bell state. Yeah. Yeah, both observables have expectation 1, so it's about there. All right. So before going to measurements, I'll show you how, because register is something physical. It's a physical system. We can specify background noise for that system, and QuantumSavory will take care of evolving that system according to that background noise. And the way you do it is, again, at initialization. So our noisy register. Let's see if I have a shortcut. Yes. And put it here. Oh well. Noisy register is equal to a register. Register with 3 qubits. We accept that it's going to be quantum optics representation, and we specify the fact that they should have a T1 decay model, and we specify the decay rate, so say 0.5, and the time unit is up to you. This can be 0.5 seconds. It should work, yes. This means that if time evolves in the simulation, a T1 decay model will be applied on qubits. All the 3 qubits in the register. Of course, you can vectorize and specify different decay models, different noise models for each qubit in memory. We have a bunch of those. We have T1 decay, we have T2 dephasing, T1, T2 together, depolarizing, so on and so forth. So now measurements. Just copy this. Oh. So measurement is pretty straightforward. You initialize, yet another register. We initialize it into the belt pair. This we already did a bunch of times. And we check if this is assigned. It's not actually the measurement. There it is. So if you remember, if you call observable, we just get the expected value of the observable. We don't actually measure. Oh yeah. We don't actually measure the state. So if it is assigned, it's still true. However, the actual measurement is called project trace out. So you actually measure the state according to some observable that you pass, and then you trace it out of the state. So if we create a register, initialize it in Z2, so one state, then we project and trace it out in the Z basis. Then there is the outcome is 2. And if you is assigned, it's going to be false because you measured it out. Instead of the explicit basis, you can just also pass the operator. See why it doesn't like it.
You already measured the state.
That's fair because it's not assigned anymore. Yes. Yes, this works.
What do you mean if it's in that basis?
Okay. Let me see. And I'll conclude this part with something that will wrap everything with it a little bit together. That is defining quantum circuits. So we saw how to initialize, manipulate, measure registers. So the way in QuantumSavory you think of a circuit is basically a function with a bunch of operations and some measurements at the end, and you return the measurement outcome. That's all a circuit is. A quantum circuit is in QuantumSavory. For example, a circuit that prepares a bell pair for you could look like this. Initialize, you apply Adamar and C0, and you return nothing because there's no measurement going on. QuantumSavory gets shipped with a circuit zoo, which is a bunch of ready-to-use circuits. So, operations, for example, spanning from entanglement swapping to distillation, a lot of things that are pretty commonly used in quantum information science. And you access it like this, and you can get any. Like you can use them directly. In this case, we're going to use the super dense coding circuits, so for encoding and decoding. So the way we do it, we create our registers at Alice and Bob. We prepare a bell pair between Alice and Bob. Then Alice encodes a message, and using the ready-to-use black box encode circuit, which is nothing else but a wrapper around some sort of function that looks like this. And then Bob decodes it. It reads the same message that Alice sent, and everyone's happy. Let's see if this works. Okay, yeah, so everything works. Okay. So let's finish with the quantum modeling with 5 lines of code that basically should get us up to date with the first part of the initial example we saw, that is the register net. So the register network simply puts together a bunch of registers. And you can check the documentations. You just look up QuantumSavory, and there is the API. You can see all the different parameters you can pass, but 99% of the time, you're just going to pass the graph, the topology, the list of registers you're working with, and you can specify a classical delay for classical communication. So every time you send a classical message from node A to node B, you will apply the specified classical delay. You also have options to set it so that it matches the length of the links in kilometers, like speed of light propagation delay. And the way you create and send classical messages, we're going to see it later, but I'm just gonna do a little spoiler. You can create channels from the network. So this is a classical channel connecting node 1 to node 2 on the delay network that I just created. So this channel here is basically not a channel, it's basically a path, because node 1 and node 2 don't have to be connected. So it's a path connecting node 1 to node 2, and if I feed something into that channel, will be delivered from node 1 to node 2, and QuantumSavory will take care of applying all the classical delays that make it realistic according to whatever you pass to the network. So that's it. And let's take 5 to 10 minutes break, and then later we're going to conclude and go back to the initial example.
Okay, so okay, so we saw. What is this? Yeah, right. That's my swap. Okay. Skip that. Just write this. And symbolic. So symbolic is just like, look, you can type these things.
Yeah.
Symbolic.
I think symbolic is just what I'm preferring.
And then we wanted to register, which was showing how big the register is. So like the qubits and initialize them, they can be in build codes and
Yeah, and Grace.
In constructing the network, like obviously there's exceptions for repeats, it's like helps against it.
or no.
Yeah, no,
it's
no,
just
no. I don't think we have these samples. We didn't show any.
anything like that, right?
Yeah.
But he did say something.
Second zero, yeah.
Oh, he just said it exists.
Yeah.
That's augment like different.
I think very much.
Maybe. I guess the team. Because he kind of skipped over.
I don't know. This
And then he mentioned background noise, right?
yes.
So here's the one here. You mentioned that, right? That you can
Yes.
Yes.
Oh, yeah, equal sign and then, yeah.
Okay, so
I thought you were telling me that that was a greater than. I was thinking, no way, what's a greater than? What
I'll
the
try
hell
to,
kind of
like,
notation?
So
Like, I see what you mean, it's like, it's doing the thing where it's.
Right, so the closest particle spoke, what three hours.
Yeah, because they didn't write anything else in the clicker.
Mono has.
That's like 7 minutes more weight.
So,
The side one,
yeah,
like
I mean,
that.
this is one example of how they.
It's the same.
By the way,
I think I was
Like,
Then noise. It's just
by the way, I think it's already
But I want to look at that.
Yeah.
I
His name was quantum
Yeah,
symbolic.
it's probably not that.
Oh, that's fine.
Second of all.
Two.
Second of all.
Yeah.
Yes, you do. Just assisting them.
Was it like this in the?
I don't know,
first half as well?
what was.
No, there is.
General procedural.
Just because I remember.
inconsistent.
Wait, was it Maya?
It's also, it's
Oh,
not a-
wait, but if you still wanna have like dinner,
Oh,
some
so
whatever
like
you want, whatever else, whatever at the same time.
Two of them getting together. Should just work.
See this?
And the PR.
It's almost like a joke that became.
Now, yeah, we have.
Oh, you say that?
Maybe it wasn't like that.
Right, it is.
It's actually how we generate our table of like real.
Honestly, I feel like that's one of the few things that will motivate me to do that. I spent some time doing it when I finished my masters because I think,
So no transport and then like
like everything in
and
line
then
for
this goes
like
again,
ChatGPT
and then
is all
notice code.
generated because I
like 2
don't
minutes there,
want to spend time.
notice code, like when there's restart.
Self-organized social activity.
I found that.
Both was good, but yeah.
This is the next step. This is before.
I'm raising an issue, first issue.
So I think it was 2 transfers.
Oh.
Yes.
If-
Worship.
That's cool.
but I don't know.
Wait, oh, I thought you were just like joking. Oh, really? Yeah.
It's like,
I'm not saying that
It's 7:50. If you just go to.
I was thinking maybe we should just say that we.
I can learn from you.
Yes. It's urgent issue, then you
Say this.
that you triage.
I put the issue with call, so what do you should?
Sort of. Focus on.
7:50. Yeah.
You were always on the phone, always on the phone.
So is it tonight?
What is the one that's upstairs?
You were always on the phone.
So it gave me three options. Why? feature or
And
not?
you just saw like this is where
Oh, we were standing in front of the.
I think why she's just trying to get this one. I told you that. So I really at some point come with me. She's gonna use solid to get her.
So you didn't look back? If you, you know what happened?
What type of network?
Those ICTs.
So now I know.
First, someone will
Oh,
reply
you
to
said
this.
already did.
Yeah, I did.
And then, and then, I mean, they'll merge it.
And you
just need to put it otherwise.
no, she is
Yeah,
forever
but it is
on her
possible
phone.
that someone will give you
For
a
sure.
certain way of doing it.
This is the thing about
Sorry,
source
no,
right
no,
now.
I'm just
someone
Oh, but then I can just change to here.
maybe.
No, but why?
Oh, okay, so do you think I should just wait until?
Because sometimes what we do with Entanglement have like there's some tests.
Yeah.
Run all this and then if it passes, wasting all this.
So I'll just wait until like someone calls.
Maybe until Monday or something.
Stefan, like, yo.
She's like, was being polite.
I shouldn't exist. Do you think that's enough to get me a short apple?
If you fix this, if you fix this maybe.
I mean, I waste 2 hours or I waste.
You can put it in a line. Fix here.
Wait, are people doing something?
But we were thinking of doing.
Oh, I wasn't.
That's why we're not taking it. But this is still organizing committee. Now you are putting PR.
Thanks for that.
Now we are going to
No,
merge
thanks,
PR.
thanks.
You are
I'm not
merge
good
the
enough.
PR.
I'm sorry, I'm not good enough.
Glad we don't know where we're going, bro.
Yes, I will come.
That's what I told you now. Now we are going
My
to.
heart's shattered.
No, we're going
You can
to
never be
decide.
fixed.
Now we must decide.
I don't live in UMass.
We'll get to that. What is the hurry? It's like not like 2 p.m. 3:30.
It's shattered permanently.
It's like before.
It can never be fixed.
See, that only your work was.
And that's why you leave. Go to UMass. Stay here. No,
I
not
want the
the
beer. I want the
Please
beer.
invite. Please tell Atul. We're like we're working on a program, and then I can make it to the thing. I can go every day.
Okay, sure.
You can make up for what you did.
Okay,
Invite me.
sure.
You can make it.
Even EB.
Invite me in December. We can everything will be forgiven. Forgive and forget.
In December, okay.
Forgive and forget.
Same thing.
He shattered my. He backs up. The D-stab.
D-stab, yeah, D-stabbed it. You were stabbing, he was stabbing you, now I D-stabbed.
He broke my heart. He shattered.
I D-stabbed it.
Why is temporary with that? Why is immigrant? Why for immigrant?
That is my first issue.
You did? Nice.
And he got one.
Thumbs up.
So I made up for it.
No, you didn't make
I
up for
did.
anything.
I made up for it. No, that's what thumbs up.
Thumbs up is?
Yeah, so I made up for that.
You didn't make up for anything.
I made up for it. So that thumbs up made up for
I
it.
will never forget.
It'll never be the same.
Yes. You know the experiment, they go crush a bottle and like, yes.
Pretended I was had to give the interview again.
Where's the
I don't know, he said I'm done. And he left.
with more?
I don't know, he said I'm
Giving
done.
to
I
Iran.
need that. Let's see you in Maxwell, girl.
From like
Big fight from
Huh?
It's like I'm breaking up with
You
you.
think Suraj would ever be like done and
It's better not to.
Maybe when he's like, I guess, 450 of it.
Yeah, it's fine.
Yeah, there's time for this. Maybe it's like already
Yeah,
working.
don't leave.
I think that we checked out.
Oh,
I will come back every
going
time.
back to it.
Like, and Vicky's
Every
like,
time I go to close, but
Ambiguous? No.
No.
As you have.
No, and he just went back. No response, no justification.
No, like I don't work
Like
in
it was, I've never seen him
Wait,
do
in
this show.
5 years you can start to work right now.
Man, I get like one word answers all the time.
No,
So what I think is that how did you ask this question? You wanted to discuss it?
I have
no, but more power to you. She was like, bro, so what do you do? I'm like, I support you.
Well,
I figured he could take it.
Yeah. No, he's
8 years.
I mean, he can sit with me
Yes,
like
it's
5 days in a
right.
row. I think he can take anything.
Maybe that's why he was
How do you
gone.
annoy him?
That's why he was, I think he's gone. Oh, he's back.
Yeah, no, he's sitting outside. He said I'm done and he's went.
He came back.
It starts from the hardware.
Buddy.
And everything. I even built
He's undone.
You back?
Oh,
it's really fun. No, it's really fun. Really typical physics.
He's just standing outside the door. Yeah, so he's in a superposition. I like him. He's insecure workman. What?
Well, I can just see that's good.
That's it.
Well, I remember back when we lost the research to use spread enough that's the reason we lost. I was like, no man, we lost it was like oh man, I'm sorry.
Let's start back. So we covered how to model quantum states, how to manipulate quantum states, and put them in registers. So now from that moment on, the quantum states are taken care of. Like they will evolve over time. The backend, the numerical backend will do its job, will evolve them, and then and at the end of simulation, the states will be taken care of. What's still missing is what we did in concurrent sim earlier. So remember at the beginning we were talking about the quantum modeling and the discrete event simulation part of it. So now the discrete event simulation part, it's what we're still missing. So that's with concurrent sim, we ended up the lecture by seeing that the most elegant way of doing things is having processes synchronized through resources and stores. And while these are powerful, like in theory they allow to do everything, they're still clumsy to use on large scale. So QuantumSavory takes this and builds something more elegant and more powerful. That is the tags and queries mechanism. So the way that different protocols / processes in a simulation cooperate is through this mechanism here. So there is nothing, you will not see any resources, any stores. It's internally, that's how things are implemented, but that's what we're never going to see them again. Someone might be happy about it. Instead, we use this framework. So the idea is that the whole simulation is a shared database. So once you install, you define the register network, right? At the same time, and that's the representation of the system. At the same time, QuantumSavory initializes a database in memory. And this database will contain information, will track the logical state of the quantum network. So say your simulation has two registers, R1 and R2. This database will have an entry will have some space dedicated to R1 and some space dedicated to R2 and other registers if there are other registers. So if at any point in time, some protocol, for example, entangles slot 1 of R1 with slot 2 of R2, the way that things might usually work, it's idiomatic for QuantumSavory. So first of all, the quantum state, if you initialize those slots in the Bell state, the quantum part is taken care of. The quantum backend will take care of it. It will know who's entangled with who, and you don't have to worry about that. What I'm talking about now is how to logically inform, classically inform other nodes in the network of what's going on in a realistic way. So the protocol that entangles R1 with R2, slot 1 to slot 1, might want to advertise this information to whoever is interested in it. So what this protocol, say an entangler protocol, once these guys are entangled, it will tag, and that's the API. You tag, for example, register once, tag register 1, the first slot of register 1 with whatever information you want. Since I just entangled this slot to R2, I might want to, I don't know, the format here is completely up to us. I can define a symbol called entangled. So I'm basically advertising the fact that now this slot is entangled, and I can put a number afterwards, say a string R2. Okay, now I'm advertising that this slot is now entangled with R2. At the same time, it might make sense to also advertise the opposite thing. So you might also want to tag R2 of 1, of the fact that now it's entangled with R1. Once you call tag, the QuantumSavory saves this information in the database. So there's going to be an entry for R1 that has slot index number 1, and then it stores all this information you put in the tag. So you're going to save some information here. You're also going to save some information on R2. And that information is there. If later on some other protocol wants to retrieve that information, because maybe there's a swapper that runs an R2 and wants to know if R2 has any qubit entangled with R1, because maybe I want to use that qubit to do a Bell state measurement and swap it out. So we might want to know if there's someone entangled on R2. So the way you do it is by query. So you query, I want to know from whom? From R2, if there's any slot that has a tag of type entangle, then we know, because we defined the tag format, we know that the other field would be who that slot is entangled to. And do I care? Maybe I don't care. In that case, I just put a question mark. Whoever is entangled to, it's okay. The return value of this will return any matching entry in the database according to this query. In this case, there's only one matching entry. It's for slot 1 of R2. I know the slot 1 of R2 matches are queried, so I retrieve that information from the database. And then I can do whatever I want with it. So this is this entangler protocol that tagged these slots with this information, and this swapper that query for that information, they never interacted directly. They just interacted by publishing some information and retrieving that information through a database. They didn't have to know about each other. They never will. And that makes designing your simulation much simpler, because you don't have to wire protocols back together. If you want to integrate protocols in the simulations, they just have to agree on the API of the tags that they are using. And that's why things work so well. The example I showed you at the beginning, all those protocols, they agreed on a predefined set of tags. They kind of look like this, honestly. There's a little bit more fields for tracking and stuff, because you might sequence numbers, you might need a little more precise information. But at the end of the day, if they agree on a predefined set of tags like this, and they have a shared API, they publish information, retrieve it, update it, and that's it. And that's mostly it. You use tags and queries also to send messages from one node to another. Remember at the end of the earlier part, I showed you how you define a channel from node 1 to node B. So you can put a message in that channel. And that will deliver. So let me take a step back. The database entry for our register 1 has a bunch of space saved for all the tags that you store this way, by tagging it. There is also some reserved space for a message buffer. Which basically all the messages that are being sent to R1 will be stored in the message buffer in a very similar format. They're also going to be tags at the end of the day, and they are also retrievable through queries. So it's the same. The only difference is that to put something in the message buffer, you call, instead of the tag function, you call the put function. So first you retrieve, I'm going to show you this in the code. First you retrieve a reference to the message buffer of that node. Then you put a message into that message buffer. Or if you want a shortcut, you just put a message through a channel to that node. QuantumSavory will be smart enough to wire that to the message buffer of that node. And that message will end up in the message buffer. And then if you want to retrieve messages, protocol can query the message buffer. So instead of querying the register, if you want to retrieve messages, instead the API is the same. Instead of querying the register, you query the message buffer of the register. So it's going to be MB or message buffer of R2. So now instead of looking up information published directly through tag, you're querying for information that is basically a message that you received in your message buffer. And that's, so if you want to implement classical delays and stuff, this is the way to go. If you just care about making information available right away, probably you can just stick to tags and only tags and queries, and you're good. So this is the spiel, as Stefan likes saying. So let's go back to some code, because now we're just going to show you this API in action. Let's see if now it works. Yes. Okay. So we're using QuantumSavory. Specifically, we're using the tag API from QuantumSavory. Yeah, as I showed you, right? So I can instantiate a tag. For example, I can put whatever fields I want. Say I put a symbol as the first field, because usually the first field of a tag, you want to put a label. You want to inform what the tag is about. It's like the header of a packet. You want to say this tag is about, I'm publishing information of a kind entangled with. So I want to say that someone is entangled with someone else. So usually you do it through either symbols or types. So I could define, instead of using a symbol, so say I have symbol, and then I say, and I'm entangled with node 7, slot 1. So this is a way of publishing some information. Alternatively, I could define a struct entangled with, and I put two fields, node and slot, both integers. And then I can do this. Instead of using a symbol, I just use the data type of that struct. These are perfectly equivalent ways of doing the same thing. In production, we tend to use this version here, because then from the tag, you can instantiate an object of the struct type, and it's easier to work with. But both are perfectly viable. It's up to you. So once I create a tag, you can basically tag some register. So I create a register with 2 qubits. I can tag. The second qubit, the second slot, with this. Now I publish this information. Now later, if someone wants to know is there anyone in that register entangled with node 7, for example, what I can do is query. I'm querying register because at this point I don't know which slot, right? I want to know the slot. There's something I don't know yet. I'm querying register, and the question is I want tags of type entangled with. Right, so I use this symbol. I want slots that are entangled with node 7, so I fix that field. And for the last field, I mean, I don't care about the slot, right? That's what I want to know. So for that, I can use a wildcard. So I can either use W, that means any value is okay, or I can use the emoji question mark. I never get the right slash in question. Yes, it also works. So if you look, if I run this query, let's look at the return value. Okay, so we're gonna have this reference to the slot, which is the second slot of this register here. This is the ID of the register. This is the unique ID that's given to the tag, which is useful for indexing purposes inside the logical database in QuantumSavory, and it's also useful for reference. If you want to delete a tag, you can also delete a tag by ID if you want. And then the third field of this tuple is what you actually care about. I mean, you also care about the slot. The third field is the tag itself. And this is where you get the information. From this return value, I know that the second slot of this register matches the query I made and is entangled to 7.1. So the first slot of node 7. So I have the information, I can do with it whatever I want. So that's it. And also it tells me at what time that tag was put in memory. So I can also use that information to track time, not to track time, but to have, if I needed it, I can do something with it. I can plot statistics or whatever, do whatever I want. This is mostly, honestly, this is mostly it. There isn't, okay, so let me show you this. When I query, as I show you, I can query, for example, I want to know if anyone in any slot in the register called red has a tag of type ready. And let's assume the second field would be another register index. So I don't care about that, I put a wildcard. We know that we can do that. However, I could do this with entanglement. So that's consistent with the previous example. Node 7, W, all right? So this is what we already did. However, I can also do the following. If I want to put some constraints on, for example, the slot to which we should be entangled with node 7. So I want someone that is entangled to the third slot of node 7 is not fine. I want someone that's entangled to slots that are above 15 in node 7 for any reason. So here I can also put a predicate. So I can put a condition. It has to be greater than 15. And this will only match entries where the slot field is greater than 15. This notation here, this guy here returns a function, a Boolean function that returns true only if the argument is greater than 15. So yeah, that's it. Wildcards, predicates, fixed fields. So you fix the fields that you want fixed. For example, I want to look for tags of this kind with this fixed field. You put wildcards and predicates where you want, where you have, where you are allowing multiple values for that field in the tag. A little variance on this API. If you want to query and delete the entry at the same time, that's pretty common. You query delete. Okay? And then you pass at the same thing. If you want to query all matching entries, not just one, you query all. That's it. And if you want to delete a tag, you untag. And the easiest way is to pass the register and the ID of the tag. So there's no tag of index 1 apparently. Anyway, if you pass the right index, so first what you do, you either query delete, that will delete the tag for you, or you query, you retrieve the tag index, and then you untag the tag with that index. That's how you proceed. Oh yeah, another thing is that by default, when you query, you can pass you can filter based on all the tag fields that you want, but at the end, you can also, with the keyword value, you can also put additional conditions. For example, I want only entries associated to slots that are assigned. That means that there is a quantum state inside. So I can put assigned equal true here, and I'm sure that whatever gets returned, it's about a slot that's currently being assigned. There's a quantum state in that slot. So for any reason I need this here. Another one of these is locked. Lock equals false. Because protocols, as we'll see in a second, can lock slots to have mutex access to that, so that they're sure no one else is using that, applying operations on that register slot at that time. You can also check that when you query for it. Yeah, this works. And this is pretty handy. Now, so as you remember, why were resources and stores helpful in concurrency? Because you could yield on them, right? I could yield on a get, I could yield on a put, and that's what would drive the actual synchronization. It turns out you can yield on a query. So I can, so if I query, I get a snapshot of what's currently in the database, right? I look at this query. If there's nothing matching, this just returns nothing. But I can force to wait until there's someone there that matches those constraints. So if I want to do that, I can do yield. This is going to be within a reusable function. Yield on query wait. And then same API. This, if you do this within a process, you basically are waiting until this query wait returns something that's not nothing. That's how you interact. Like a swapper will do this because it will query wait on 2 qubits being present until it can swap them. So that's an easy way of implementing a swapper. So most interactions are going to be based on yield query wait. Or more in general, say if you don't want to wait on a specific query, you can yield on change on a register or on the message buffer of a register. This basically will make that process wait until something changes, anything changes in the tags or in the messages of this register. So basically, you are waking up only when there's something new, and at that point you can rerun your queries and do whatever you want. So if every time loop you have to do more than one query, you can do this and do all your queries and then go sleep again until something else changes. So this is the most common interaction. The only yields we're going to see are this: on change, query wait, and finally yield lock reg of 1. So if I want to apply a Bell state measurement, for example, on registers 1 and 2. Oh, wait, sorry, this is not the right way. I lock this and lock the other one. You can only lock one. So this will put the process to sleep until it will be able to register the first and second slot both of this register. And this is very helpful because that avoids all races as it was worried about before. This simplifies that a lot. So now, once you have a lock on register 1 and register 2, you're sure that no one will interfere with what you're doing. You have complete ownership over those two register slots. How is this implemented? I suspect this is going to be a resource with one token inside. Simple as that. All right, so this might have been a lot, but now we're ready to put everything together. Everything that we have seen, we're going to put together in an example. Now it's going to be pretty full stack example. We're going to be a little bit more in depth with respect to the first example we saw, because we're actually going to implement our own protocol for a repeater. Where is that? It is. And for the first time now, I'm going to go through the code because it's a little too much to type together, but I'm going to go slowly down. So we import all of our stuff. We import reusable function, concurrent sim, blah, blah, blah. So what we're doing here is we're implementing the protocol that runs at each one of these guys, the swapper protocol, okay? It's a little different variation of it, because instead of swapping as soon as you have two bell pairs, it waits for a swap request. So it assumes that someone is requesting you to swap, so it's going to be a request-based swap. So you wait for a request message, so we put some messages in the simulation. So you wait for a message, then you wait to have two bell pairs ready, and then you swap them. And then you sleep until you get a new request. Conceptually, it's pretty simple. So the topology is going to be as simple as possible. We're going to build a repeater and a register network with only 3 nodes. Yeah.
When you call the classical delay, do you assume that the communication between any two nodes is the same?
Yes, it's a constant value, so any edge in the topology is yes.
So sending a message from node 1 to 2 takes the same time as from 1 to 2000.
No, because if you send from 1 to 2000, we'll find the shortest path according to Dijkstra, and we'll apply the delay k times with k is the length of that path. Yeah. So we create a register net. So 3 registers, 2 qubits each. You already see this. We create a register network on a path graph. That's another way of instantiating a chain. With those registers, classical delay fixed. We get our simulation. All right. We initialize our. We don't have the entanglers. For simplicity, we just put some bell states already in the memories. So now this is something that comes up. Remember when I told you that the tags that the protocol suite uses is a little more complicated? Because I was showing you the entangled with tag, right? I can imagine when I'm entangled with someone else, I publish that information as an entangled with tag, and I have to put as information who I'm entangled to. This is what we're doing. So this entanglement counterpart here is exactly that. this tells you that the first node in the network, so the first register, the first slot of that register has an entanglement counterpart tag, which marks that it's not that the slot is now entangled to someone. It's actually entangled to node 2. It's entangled to the first slot of node 2. And this is the additional field that I was talking about. You also need a unique ID for that bell pair that is going to, so say that slot later on gets measured out and I receive an update for that bell pair, I still need a way to map that old message from the bell pair that already swapped out, and that's where this ID comes from. Because if that in the meantime that slot gets replaced with a new bell pair, I need to understand that that old update refers to an already swapped bell pair and it's not applied to the new bell pair that it's in there. That's a bug that was actually fixed a couple of weeks ago that drove us crazy with QuantumSavory. And we introduced this UUID mechanism to prevent this kind of inconsistencies. We don't have to go more in detail than this, but we need it. So we can right away publish these tags because we already created the entanglement, right? Otherwise, it would be a burden of the entangler protocol to create these tags every time that you generate entanglement. So we create our network and we get our simulation. Okay. So after we do this, so let's run this. So what will these queries return? So let's see. We are querying the first. So let's first of all, who are we entangling? We are entangling the first slot of network 1 with the first slot of network 2. And the second slot of network 2 with the first slot of network 3. So draw it. We have now entangled first slot of this with the first slot of this. Second slot of this with the first slot of this. This is what we have done. Okay, and we have advertised this information. So now I'm querying the first slot of network 1. I could drop this. I don't need this. I'm querying the first register in the network. And I want to know if there's any entanglement counterpart tag on this register. And specifically, I'm looking for slots entangled with node 2. I don't care which slot of node 2. And I also actually don't care about the pair ID. Who cares about the pair ID? So if I run this, I need to shut up the compile again. Where did it go? I lost it. Thank you. Okay, what's wrong? Oh wait, I was editing. Wait, I was setting this instead of the query. There you go. Okay. Yeah. Okay. Yeah. I already did it properly. Okay. So I'm querying network 1, first register. I'm querying for an entanglement counterpart kind of tag. I care about only of entries that describe entanglement towards node 2, because that's the central repeater. And I don't care about nor the slot nor the entanglement ID. So if I run this, I should get there you go. If I run this, I get so the slot that matches this description is slot 1 of node 1. The ID of this tag is 6. Not that I care about, but if I want to delete it, I can delete it using ID 6. And the actual tag tells me that we are entangled to the first slot of node 1 or node 2, so to 2.1, with some entanglement ID, for which probably I should post a PR for printing it in hexadecimal, because that would look better, at time 0.0. So that's all this is. Again, our observables are fancy. Let's now see together how you define your custom protocol. So we now have our entanglement. We are assume this is analogous of having an entangler protocol that creates those helpers for you, right? Let's create a protocol that swaps now. The one that the QuantumSavory comes equipped with is called swapper pro. So here I call it my swapper protocol because it's our custom version of it. So this is how you define your own protocol. So basically it's a struct, so you have to create a subtype of abstract protocol. And this is the context that's going to be available to that resumable function live while it runs. So it's a fancy way of giving context to a resumable function. And we want to, otherwise you would have to pass these as parameters to the resumable function is all. It's like the same thing, it's just different formalism. So this swapper runs on this simulation for a specific simulation on this specific network. So it runs specifically on this node, and it wants to entangle Alice with Charlie. Okay, these are all node identified, node indices in the network. And then we make this structure, we make it callable as a resumable function. So this syntax here creates a resumable function that's callable as, so if I create an instance of my swapper protocol, basically, like this, I pass all the parameters in here, then I can call it. And that's a resumable function. That's how, and to create it as a process, you mark it as a process. So that's how you use it. Okay, and this is what this function here allows you to do this. Allows you to do this. And the code itself is actually pretty simple. First of all, we unwrap the context of my swapper protocol. So we have all those variables available. We get references to two things. We get references to Bob as a register, because right now we have the index, right? It's node, but we want to actually access the register itself. So we get node index within net. And we gather also a reference to the message buffer of this node, because we want to query on it. We want to check when we get messages, right? And that's it. That's what I was telling you before. Now it's not a query wait, it's a query delete wait. So we wait on the message buffer. We wait for incoming messages at our node of type swap request. So the messages should have only one field of that, where that field has this value, swap request symbol. And we wait there forever until there's something that matches this. And when that happens, we query and delete it. So we also consume it. So we're not going to query it again by mistake. So we get that message. So once we get the swap request, we can query for the actual qubits, see if they're available, and if they're available, we swap them. So now we are allowed to proceed. So now what we do, we query and we see if Alice has, if there is a viable qubit entangled with Alice. So we query ourselves, because we have to query ourselves. We want to see if there's any entanglement counterpart tag entangled with Alice. I don't care about the slot of Alice we're entangled to. I don't care about the entanglement ID. Of course, that slot shouldn't be locked because someone else is using that slot. Maybe another instance of another swapper. We don't want to overlap with them. And it should be assigned, right? Same thing for Charlie side. We want to query. It's the same thing, but instead of being entangled with Alice, we want a qubit here, local, that's entangled with Charlie. Now, with this specific simulation, these queries should always return a value because we manually injected those tags, so they should be there. So we just assert at least not return nothing. And now before swapping, this is very important, I lock those two qubit slots. I lock them because to apply operations on them, it's good practice to lock them. So I know that I'm the only one that at this time, I'm allowed to apply operations on these two qubit slots, memory slots. So we lock them. Now, once we have locked them, we might have been waiting here for a bit because say there's someone else, when I was here, I don't have ownership on those. So right now, in this point in time, they could be chosen for swapping. However, there might be someone else that tried to lock them at the same time. And I have no guarantee that I was the first one having access to them. Those might have been given to some other protocol that measured them out for other purposes. So after I lock them, I have to recheck the query condition again. Because time might have passed, those queries might actually yield different results right now. So I requery the same exact query, and I make sure that queries are not nothing. Okay, I requery again. I want to be sure, super sure that no one touched those qubits in the meantime. If someone did, I basically unlock those two qubits and start again. Now, there is no while true loop here because we're only doing it once, but ideally you want to put this in a while true loop so you keep waiting for requests and swapping. So here, if those two slots had been measured out by someone else in the meantime, you would just unlock them right away and continue to the next iteration because you couldn't do anything with them. So now at this point, we have ownership over the qubits. We know that no one has touched them. We can swap them finally. So we remove the tag because we queried. We didn't query delete. I could have queried delete here, I guess. Anyway, we untag them. And then we use the circuit zoo. Remember the circuit zoo or quantum operations already implemented for you? The circuit zoo offers a Bell state measurement circuit that's called local entanglement swap. So we just call that and apply local entanglement swap on qubit Alice and qubit Charlie that are stored locally above. That's basically a Bell state measurement, which returns the 2 bits for the X and Z corrections. I won't go over this. This is just a way to update the entanglement IDs because now you swap 2 Bell pairs. Each Bell pair had their own entanglement ID. You are creating a new Bell pair. That new Bell pair will have an entanglement ID that's a combination of the 2 entanglement IDs for the 2 composing Bell pairs. So that the new Bell pair will have an ID that's a hash function of the IDs of the Bell pairs you stitch together. So now we have to, entanglement swapping is not complete. We did the Bell state measurement. If you remember from that picture, we need to send the classical information to the nodes. And so we send a classical message. We send this information here. We need to send these bits to either one of the 2. I think we are sending them to both in this case. So we use the interface we saw before. So we put something. We put what? We put this tag here, and this is just going to be our message. We just specify that this is an X swap update. It means that you want to apply an X correction on what slot at Charlie, and you give the information about who that slot is now entangled to. At Alice, so you're updating them, right? And they say you're not entangled to who you thought you were entangled before, you're now entangled to someone else. And this is what this information tells them. And then blah, 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 the actual correction and so on and so forth. And this is pretty clever. We're sending the X update to Charlie and the Z update to Bob. To Alice. So we are sending one message, two different bits. We're sending one one way and one the other. So Alice will be in charge of applying the Z correction. Charlie will be in charge of applying the X correction. That's smart because you have to inform them also at the same time you have to inform that they're also entangled with each other. So you're also splitting the correction bit so that also the correction will be split among them because you had to send them a classical message anyway. All right, so we did the entanglement swap. So this is a circuit. At the end of the circuit, those qubits get called project trace out. They get traced out, so they're not in the memory anymore. So they are unassigned at this point. The last thing you need to do, okay, I did everything I had to do with those slots. I can unlock them peacefully. And for whatever reason, return these two values, not that we need them. I could have put nothing here. And this is my swapper protocol. Nothing more. If you look at the actual swapper in the protocol zoo, it's a fancier version of this. That doesn't wait for classical messages before swapping, because that's not how it's defined. It just swaps as soon as it can. There's more fancy thing. It will there was filters on what slots you could swap, so it has to check for those. But at the end of the day, it's a more articulated version of this. Yeah, that's it. And then we just need to have some process at the endpoints that receives those updates and does something with them. So we have another process. In this case, I didn't create an actual protocol, just to show you that we can do things either way. I went back to using a reusable function. So we had another process. We're going to instantiate this twice, one at Alice, one at Charlie. And what this protocol does is basically look at their own message buffer, and whenever they receive an update from the repeater, they know that they're now entangled end-to-end, and they can apply the correction, and then life is good, and then they can print out whatever that they are happy. So we get a reference to our own mailbox, message buffer, and then we query wait. So we wait until we receive a message on that message buffer. Now, given the way we define simulation, we know that the only possible message that we might receive is a message of this kind, an update tag, right? An update tag which I pass as a verb, because Alice always receives update Z. If you look at this, Alice always receives this. Charlie always receives this. So I can instantiate the receiver so that they know that they should only query for this kind of tags, respectively. Right, so Alice, so they wait for one of those updates to come. Then they use the information in the tag to make the code readable. I just assigning the tag values to actual name variables so they're more readable. So you see, Alice thought she was entangled with this guy, but now she's entangled with this guy. And all that information is present in that message. And now she's entangled with this new remote slot and this new remote guy. And that message also contains a bit that tells her whether she should apply a Z/X correction or not. So then we replace the entanglement counterpart tag at Alice's because now we have to update it, right? So we have to reflect the fact that we're not entangled with the old neighbor anymore. We are entangled with the new remote node. So we delete that tag, the old tag, and I could have done this later, but we delete the old tag. We apply the Pauli frame correction based on the X/Z correction we received in the message. So you see, if it was a swap update Z and the correction was 2, then we actually apply the Z gate. If the message was actually of type swap update X and the correction bit was set, then we apply the S-gate. So at this point, we restore the bell-pair in the 5+ state. The last thing to do is to retag that slot to publish the semantic fact that that slot is now entangled to the new remote guy after the swap, right? So we tag the same slot of the old tag with an entanglement counterpart tag. For this time, we want to say that that slot is now entangled to a new remote guy, to the new remote slot of that guy with a new pair ID. And that's it. That's all the end node does. And now we run everything. Yeah, everything worked. All these assertions work. Let's see what they do. What was Alice's final? Oh yeah. We inspect the result. We check that Alice has the right kind of tag at the end. Specifically, we check for an entanglement counterpart tag at Alice with node 3. That's Charlie. We want to check that there's someone entangled with Charlie at Alice, and there's someone entangled with Alice at Charlie's. And both are present, so good. That's all. And I hope this gave you an idea of what's the right idiomatic way of setting up interactions between protocol and synchronizations within QuantumSavory, because this is specific to entanglement distribution, synchronizing swaps, etc. But this applies in general in any kind of LCC where you have to wait on conditions to realize messages to arrive. That applies really, really in general, even outside quantum networks, but QuantumSavory is for quantum networks, quantum systems. So that's what we are going to use this for. Yeah. And material-wise, we're done. What I want you to encourage to do is to go together and take a look at the documentations. If you type QuantumSavory on Google, here's the docs. So we have to update them. This is the old version. You have to go down all the way here and click on dev. Otherwise, you get the older version. And reminder for us to update the docs. And here, if you will find many tutorials if you want to get started and start doing similar things, things that are similar to what we did today with incremental level of hands-on. But also, what I'm going to go over now, the explanations. And mostly, actually, the references. Yeah, because I want to give you a pointer to the Protocol Zoo APIs. There it is, here. Okay, if you remember those entangler protocol, swapper protocol, entanglement consumer, entanglement tracker, they have to agree on a predefined set of tags. And those standard tags are actually stored in this other entry, standard protocol tags. And here you can check what they are and what they do. For example, entanglement counterpart, which we just used. So if you want to inject your own custom protocol within that protocol suite, you have to be compatible with this standard tags, because that's how those protocols communicate. So this is the reference for that. If you instead want to check the actual complete API for those protocols, for see all those configuration parameters, what you can do with them, this is the place to go. Also, you can do it from the help shell of Julia. You can just help !entangler pro, and we'll tell you the documentations as well. What I wanted to do, I wanted to jump at entangler protocol. Here. There you go. I want you to look at entangler, swapper and entangler protocol. Here, it will tell you all the parameter it takes and what they do. And I want you to use this to remember the example I showed you at the beginning. You should have the code for that from the repo I posted. And I want you to edit that example just by playing with the configurations of the swapper so that you implement exactly the specifications of this example here. This example here told you that you had to distribute entanglement with this nested swapping order. So this guy has to swap first, this to create these two chunks. So they cannot swap all at the same time, which is what it's implemented right now. You have to impose a specific ordering in how nodes synchronize with respect to swapping. So these guys should swap first, then this guy should swap, and only then you should see the end-to-end bell curve. I want you to play with the find what is the right configuration to play with, make this happen, and then regenerate the MP4 again and check that the video actually shows that. So give it a thought.
Right? I think that's what it is. Yeah, because if you put in, here it says, you can put in like farm one, find the node furthest to the left. So then it's not just, that's why.
Right. Yeah, I do not think.
And I shall now not, but I think that's how we would do it. I guess I could have. Yeah, I didn't think of that. There's definitely something the rest of it.
Right.
It's not. It's not the same thing twice. Okay. On here. Oh, yeah. Wait, I'm just gonna update the thing in here though. Because you know they have it already. Right, like nice and buffer. So I think we changed just. Where was that even?
I think it's over this section. Yeah.
It was
Bob
the.
looks for Q Alice. See what's
Oh, but this is hard coding down to just 3.
Yeah.
So now also we'd have to make it more general.
Yeah.
It's after the.
It's something to do with protocols.
No, but we saw something more general before, didn't we?
This would be good.
Just kind of-
This protocol, repeater chain.
Yeah. Is that's because that was for general, right? And then we just need to, I think this is where we, Oh, but then it'll depend on the node.
What is this?
This one was for like 4 nodes to the left
Yeah.
versus nodes to the right. But now we need to specify it as like.
I want judgment.
swap
So sure.
Maybe I'm wrong. So I thought that if we could specify. Because don't you always swap with I guess it depends on which one you're are, right?
Judgment by credits. I need to fix this.
So we would do it like. So this is for n.
What's the syntax exactly?
Because I was like, yeah.
Anyone
Any node?
finish it already? Okay, let's put it this way. Does anyone think they found the right parameters to work with?
There'd have to be node -1. Be the adjacent.
Oh, right.
Yeah.
How many at once?
But we wouldn't work. That would enforce like you only swap. You want to have the nesting.
I swapper protocols, one for each node.
That's already like that, right? You're already instantiating 5 swapper protocols. What you have to play with is you have to impose a specific swapping order. That's what I'm saying. So you're still going to install 1, 2, or 3 swapper protocols, but you have to configure them so that you impose this specific swapping order. So these 2 guys will go first, and then once they're done, and you created these 2 chunks.
Can you just set like for the second node, node left 1, node right 3?
Yes.
And then I do the
No,
same.
it's
So
5,
for-
right? The 1, 5.
No, I'm thinking node 2.
Oh, this
Node 2 does between 1 and 3.
Yes.
Node 3 does between 1 and 5.
Yes. And this?
And this is
Between 3 and 5.
There you go. That's it. And
So
which
we only
one?
use node left and node
and
No low and no high. Yeah.
low and high.
Yeah, that's it. That's it.
So
See,
does
this one.
the choose is meaningless in this case?
Yes, because choose are about the slot. So
But I think it would be something like
Let me
that
see.
where you're like check that like for.
oh yes, no, that's how it works. So node L and node H return the valid candidates. So all the nodes that you accept. In our case, it's only 1 node, so it doesn't. The choose will not matter. But the choose then is the policy with which you pick one from the list returned by the node H and node L.
So it's for different kind.
Yes, yes. It's like if you
You
want to do
leave
it.
it
sort of-
empty, does it just,
So we need to rewrite this.
you leave it empty, does it work?
If we rewrite this.
If you leave it empty, you're it's the way it's implemented, you're still gonna be waiting on the query wait. It's not gonna be awakened, yeah.
Oh, right.
Yeah. The way it's implemented, the
The other thing doesn't have anything built in already.
because this is gonna go into some query at the end of the day.
Okay. Would be. And to ceiling. And might as well.
Well, we got our solution. Before, so for as far as I'm concerned, we went over all the things I wanted to go over. We are pretty happy. We finished a little earlier too. Do you feel you want to go again, or like you go over some specific topics that you didn't understand, or want to see something else? I'm open to it. Otherwise, we can go take the group pictures. Yes.
I didn't understand the solution, sorry.
Yeah. What this solution here for this last thing?
Yes, yes.
Yeah,
yes,
of course.
the,
So
Is it possible to code a simulation using this protocol, or does it take too much time?
If you want to implement the solution.
Yes.
Oh, yeah, absolutely. First, let me go over like why it works. So did you follow, are you like, without imposing a specific walking order, are you Are you up to date with the fact that we have to install a swapper protocol on each node here, or do you want to start from there?
Not completely, sorry.
Yeah, no, no worries. That's why we're here. Okay.
I understand like that those space is swapping in general, and like there's some order you need to do it, but I don't.
Yeah. Okay. So well, let's do it this way. So we describe our static topology. So we start with the register network. 1, 2, 3, 4, 5. And this is the register network. And we have 1, 2 guys here, 1 and 2. 2 slots here, 2 slots here, and 1 slot here. Okay. The first thing we run an entangler probe on each link. Okay. These guys are perfectly autonomous. Once they start those, they will try to lock their qubits. So this guy will work on these 2 slots, this guy will work on these 2, and attempt entanglement generation until you entangle them. So if this was just your simulation, eventually at some point you were going to have everyone, they're all going to generate entanglement at some point in time. Now you add the swappers. So you add a swapper here, a swapper here, a swapper here. That's it. So what does the swapper do? The swapper does a query wait. Ideally, the swapper does queries until so the 2 queries that you're interested in are the following. Say you're this guy here. You want to query on, say this is node N. Okay. You query register N. So we query ourselves. I want to look for a qubit that's entangled on the left. So any node that's on my left works. So I query for any tag of kind entanglement counterpart, because that's the tag that describes entanglement. Okay. The first field is the remote node to which we're entangled to. And in that field, I put a predicate. I'm okay with any node that's on my left. That's lower than N. The rest of the fields I don't care about. I put all wildcards. That's it. So this query so there is this query, and then there's the sister of this query. That's the same query, but here you have a greater than. So you want both this query and this query to return something. And you get the slot returned by this query and the slot returned by this query. You swap them, measure them out. You empty those memory slots. So once you have swap them out, these are now empty. And in the future, the entangler protocol will be able to use them again to regenerate entanglement once also the other one frees up. So now you swap them out. What you do is you create a classical message. So now you put a classical update. And that's where do we put it? We put it towards the message buffer of the nodes that we were so this guy was entangled here, so we send a message to this guy. This other guy was entangled to this, so we send a message to this guy. So we put one message update for this guy and another one for the other guy. So we send these messages out, and then we go back all the way back to we requery until those 2 queries give us other 2 viable qubits. And you do not just query, you do query wait to be sure, we wait until you have this for you. So this is how the swapper works. What I was asking for, so was right now here, this is the condition right now. So this is, as long as I have a qubit, I don't care who's entangled to, as long as it's whoever on the right, I just swap it out right away. This is called swap ASAP. I wanted to impose a specific order. For example, this guy should swap only when, this guy can actually swap whenever he wants, but this guy here should wait until this is entangled all the way with 1, and this is entangled all the way with 5. So this guy here should have, here instead of lower than n, it should have exactly 1. And here it should have exactly 5.
Right, because like that's the index of a node that must be entangled.
To be eligible for swapping.
Right.
And that parameter that here is basically taken from this. Like node L and node H. These are the two things that set that.
Right, and it's sort of in the base load, and I can't go into the specifics because that's but in the base load it's sort of implicit that when that condition is fulfilled, there are already entanglements like on the two. Right, so like you can only do that swap when. Yes.
Say that again.
I mean, so you have node 1, 2, 3, 4, 5,
Yes.
right? As far as I understand, again, this is very conceptual, so maybe I'm right, but to swap the death node in the middle one and to create an entanglement with the node
Yeah.
with 1,
And we were talking.
that
like
requires
something
that nodes, yeah, so like to like combine those two entanglements. It doesn't require that, it requires that there's an entanglement between the two already, right? So
Yes.
yeah, okay, that makes sense.
Yeah.
Okay, so just saying that you must ignore the middle one because otherwise that's there's two ways it can be entangled to the left and one of them is forbidden. So you
It's just like the beginning.
So what might happen is that when you start the entanglers, this guy is very slow.
Yeah.
And for some reason it doesn't arrive. So this guy might actually swap before this entanglement was generated. So when this bell pair arrives, the other qubit might actually be entangled all the way already up to the end node. And that's why you have greater than.
Yeah.
Because it doesn't have to be the adjacent one. It can be someone else entirely.
Yeah.
And yeah. So is that what you were going towards?
kind of, yeah, I was just wondering how. Yeah, but I think I get it because it's the entanglements that happen. So I think it's okay.
Okay.
What I was wondering is that, well, what if we had just had an entanglement on 1, right, between the 1 and 2, but none between 2 and 3.
In this case, you're still waiting for these queries.
Still,
you're waiting and you're sleeping until something else happens, so that you can recheck the condition again.
And then you are told to, okay, I must entangle on 1 and then entangles all the way through. Okay.
Yes, if this is the situation you're in, once you do your swap, everything is done. So yeah, the swapping order in this implementation here, with the one I showed before, the swapping order is random. Depends which entanglement is delivered first. Whereas what the task there was to like impose a specific ordering. Right? Was just to this was exactly my objective, like to get into it so that we understand a little bit how it works. Thank you. Do you still want to go through the solution of this? Is this okay? Yeah. I'm happy to chat though later. Well,
I guess
how about we take a good picture?
Nice.
Hey folks, I guess that's the last lecture of the day of the week. Thank you for surviving and thank you for joining us. I hope this was useful for you. We'll probably be sending various surveys asking for your help in figuring out how to make the next year better, and also asking for feedback because the funding agencies also benefit from that and it informs them how they think about funding for events of this type. The other thing to mention, it's this last June that is really behind the grant that's coming this summer school. So go ahead and start on GitHub. That's the cute little stuff like this actually does help when we're asking for help with running events like this. So what was it? Like and subscribe. And on Zulip, I messaged for potentially folks that are not around right now that will be taking the picture at 5. So if you don't mind waiting for another 12 minutes, and we'll just gather in front of the building and take a picture with the new facade. If that's okay with you folks. And again, thank you for joining us.